Okay, very good. So, I think all of these presentations always begin with, well, there's so many devices, and the nice thing about things is that there are so many of them. And this is just your common sort of growth chart. It's a little blurry, and it's even just a tad old. I don't know that I believe these numbers 100% in terms of predictions. Suffice it to say that there are a lot of these devices out there, but to put this into context, there are over a billion Android devices. There are over a billion uh, iOS devices in terms of Apple. So there's 2 billion right there, and these numbers can easily creep up, and so I've seen estimates of up to 75 billion by 2025. To me, this is not necessarily the pain point, except that each of these devices I view as a threat. So let's look at one of those devices. This is an SKG oven. It is sort of the upmarket oven that I think LG sells. And the way that I was introduced to this oven was through my cousin. Um, she was talking on Facebook about how this oven had woken her up at 5:30 in the morning to remind her that it needed to be cleaned. Now, to many of us, this would be considered a denial of service attack on our sleep. However, the key thing that my cousin didn't recognize was that even if that wasn't the denial of service, the oven was certainly possible in participating in one or capable of participating in one, because in order to take on in order to page her, she had the device itself had to have a CPU, some memory, and a transceiver. And anything that has that combination of things can be used to attack another thing that has that very same combination of things, and that can lead to two different types of risk. The first type of risk is the direct and specific risk of, say, burning my duck. And that is to say, the risk is to the person, and it involves the cyber physical activity of whatever the device is taking on. The second type of risk is indirect risk, in which the device is used to attack others. And there is a combination of the two in which, let's say the device is turned on and it heats up to, say, cleaning temperatures of 300 degrees Celsius. And not only is it turned on, but say all similar devices within the region are turned on. And let's say it's done on a hot day in the summer in, say, a part of California that might already be strained in terms of energy resources, and now we have a different form of attack. It's not just my duck being cooked, it's in fact brownouts being caused and critical infrastructure and people's lives being put at risk. Sounds crazy. It might have sounded crazier even last year, but I'm sure we're going to see these sorts of attacks on our infrastructure. We know we have people who are attempting to make these forms of attack. Now, how did this device communicate with my cousin? It did so through a common communication pattern, of course, which is that you have a device that has some sort of small stack on it. It's reporting out to a central service somewhere in the cloud, which is to say some data center somewhere. And then there's a rendezvous to my cousin's smartphone. And this repeats itself again and again. And while there might be some communication in the home, a lot of this is going to the cloud. So we'll take it. We'll come back to those communication patterns in a little bit. Let's back up for just a moment. Now, the nice thing about definitions of IoT is that there are so many of them. I doubt that any two people have the same definition of IoT, so I'm going to define it for myself for this talk, and it is we'll use scoping to just scope the definition to this talk so that you can use a different definition at another time. And so my definition is something that has a CPU, some memory, and a transceiver that impacts, detects, or affects some observable physical activity beyond itself, and has a single or small number of intended uses. Now, that latter phrase, has a single or small number of intended uses, is there because Otherwise, we can say, well, this iPhone here, it has some sensors in it about its environment. Is it an IoT device? Well, by some definition, sure, right? But it is also a general purpose computer. And I think part of the challenge that we face as engineers and computer scientists is scoping problems. And if I try to scope a protection challenge to scope general purpose computing and all of IoT, I will have effect boil the ocean that Dr. Leinen would like to map, leaving nothing left. So let us proceed on that definition. Now, a brief challenge here that we have is, well, what's the threat surface? And how do we know how a device is supposed to behave? Here you see a printer. I would like, if you could, to find a small piece of paper or a scratch pad and just take 20 seconds to ask yourself and write down what sort of communication pattern you think that printer should have. I'm just going to sit here and watch my watch for just 20 seconds. I know our time is valuable, but please just write down what sort of communication you think that printer is using. Okay, time's up. So now that you've written that down, let me show you what this one is using. So this is just a subset. Now, the fun part of what you're seeing here is, of course, the device is using, some UDP discovery of using multicast. You can see that there is some access that is needed for local networks, but this device is also, not only is it using port 80 and port 443, our classic web ports in TCP, but it's using ports 5222 and 5223, which is Jabber, XMPP, a chat protocol. And look there, chat.hpeprint.com is one of the places that that device is going to. Now, this is work that was performed by people at the University of New South Wales. The key message that I want to bring across to you is that this is just one printer. And you probably didn't write down any of this in terms of communications patterns, right? And a different printer, say a Canon printer or a Xerox printer or a Toshiba printer, they're not going to want to communicate to xmpp009.hpeprint.com, right? So we have a big problem. And it scopes across different verticals, right? Each of these devices and each manufacturer type of devices has a slightly different communications pattern. And trying to figure out the right pattern is its own little trick, because one of the key stress tests that we have is, as Anna Maria said, is that we simply cannot even count the number of types of things that are out there, right? Is a different firmware upgrade does that make it a different type of thing? It's a big challenge, right? So I set out to look at this problem, right, and to try to address this problem. And it turns out, really, there's sort of two approaches that people are tackling the problem with in order to add a layer of protection onto the device. The basis of my work is that all of these devices, all the manufacturers of these devices, are excellent at what they manufacture in terms of the primary function, right? A power meter manufacturer knows how to manipulate and measure voltage. Philips knows how to make a great light bulb. Fanuc knows how to make a phenomenal robot, right? But internet security is not their primary goal, right? It's providing the function. And even those of us who've been working in the business in IT for 30, 40 years still don't get it right. So we shouldn't expect a lot out of OT manufacturers. So they're going to need an additional layer of protection, right? So the nice thing about things is that there are so many types of them. I don't know if it's so nice. So there are two different models that I think I want to talk about. The first is that you have that we use tracing of packets, whatever we can get out of the device, whatever we can observe from the device, to determine how that device is meant to nominally behave, right? And so these are where this is where machine learning comes in. And my own company and a bunch of other companies have delivered to the market machine learning capabilities to try and at least classify what the device is and what sort of access it needs so that you know what nominal is. I'm not going to talk so much about machine learning. I'm not an ML guy. We'll leave it to others to talk ML, but I'll just mention a couple of things. The first thing is that ML, the sort of brownfield scenarios that I'm talking about here, in which the device doesn't have to change, that is to say, there are no ecosystem requirements, and I mean ecosystem in terms of network ecosystem, as opposed to, say, oceanic ecosystem. Because there are no requirements on the ecosystem, right? Machine learning is great. It steps in, it learns, it tries to figure out what's nominal. You can just use it, and you don't have to go to vendors saying, go implement this stuff. On the other hand, every time you upgrade a device, its communications patterns might change. It's also hard to know, for instance, what nominal is for some devices. Let's take one example, a smoke sensor. Maybe it sends, in nominal circumstances, a packet every 5 minutes just to say, I'm here, I'm alive, no fire, right? But what happens when there is a fire? All of a sudden, there's a change of behavior. And now we have to ask the question, is that a smoke? A, is that really a smoke sensor? And B, is that smoke sensor either still acting in a way that it's supposed to, or is that device misbehaving, or has it been owned? So machine learning will have some challenges in just how those devices are learned, right? You really have to have a clean room, and you have to exhibit all the functions of the devices, and sometimes that takes quite a lot of work. In a declared model, there's no machine learning. This is what I would consider to be very simple thinking, which is good because I'm a very simple thinker. And in this model, a device manufacturer has to declare what sort of behavior should be expected from the device. The challenge is that you have to get the manufacturer to do all of that. And this is very slow in the coming because this idea has been out a little while. So with this declared approach, right, we are making a couple of assumptions, right? And the assumption, first of all, is that the thing has a single or a use or a small number use. Things are tightly constrained, CPU, memory, and battery, and programmer time. That's a big one. And network administrators, the other assumption we're making is that network administrators are going to be the ultimate arbiters of how their networks are used. So nothing that a manufacturer does is going to impose itself on the network. Even those things that can protect themselves today may not be able to do so tomorrow because new attacks will be found, right? And we will think that we were cleverer than we actually were, right? There was actually an attack out there, and this is where the best and the brightest generally fail, right? So these are the 4 assumptions I'm making. And because of those 4 assumptions, I'm making a couple of assertions. And the first assertion is because the thing has a single or small number of uses, of intended uses, all those other uses must be unintended. And so we can block those if those uses can be mapped to a communications pattern. Any use can be clearly identified, and who's in a good position to do that? The one who built it. That actually turns out to be an assumption more so than an assertion, right? And it's something that we actually have to try to fix. And finally, we do need this layer of protection because devices will have vulnerabilities. And even if you can't update the device to get rid of a vulnerability, maybe because the device manufacturer has stopped supporting the device, maybe the least they can do is make a change to limit the profile or the threat surface of the device. So when we say that a thing has a single or small number of uses, right, this translates to access lists, either permits or denies. Here's on the left, you have what that enumeration is. On the right, you have everything else, right? And these things have been around since I was a kid. So I'm going to introduce to you this concept, which we call manufacturer usage descriptions, and it consists of 4 elements. The first is a URL as to where you go get the description. The second is the description itself, which is nothing more than a bit of JSON that's been serialized out of Yang, which is modeling language. And the thing that we built upon is an access list definition in Yang. The third is a place to go get the file, which some of us might call a web server. And the fourth is something that will take abstract policy from the manufacturer and convert it into configuration in a local deployment. We call this a MUD manager, but as you'll see, that might be a AAA server or some other component that you already have in your infrastructure. Right? The goal here, by the way, with all of this is to only increment and not try and revolutionize deployments, because revolutionary stuff usually doesn't get deployed. So the way this works very simply is that, and this is a component architecture, by the way, not all of these components need to be used in all different circumstances, but let's take one circumstance in particular. The device outputs a URL as part of its boot up process. Maybe it's authenticating using 802.1x. Maybe it's outputting a DHCP packet or an LLDP packet on layer 2. And the network infrastructure picks it up and passes this on. And now this guy has a URL. Well, what's it going to do? It does what everybody else does with URL. It goes and resolves it, pulls down a MUD file from the MUD server. And then the MUD file server has a file that contains a few abstractions. Well, why do we need these abstractions? That's because the manufacturer has no understanding of individual deployments. And this is a many-to-one situation in 2 dimensions. That is to say, there's going to be many different deployments for a particular manufacturer and many different manufacturers for a different deployment. So the manufacturer doesn't know the infrastructure, so it has to abstract out IP addresses, and we have 4 abstractions. Controllers that can be given access, local access, meaning just let me access the local network, domain-based access for cloud, so a domain name, or same manufacturer used, say, for instance, where light bulbs want to synchronize each other so that they don't create a popcorn effect where they turn on. So now we have a file that is returned along these lines. It is returned to the local deployment, who then knows which abstraction to use when. And then there's an approval step because the administrator is king or queen of his or her own castle. And then the config is instantiated in the devices to apply access lists to deliver what we call microsegmentation. And this provides an added layer of security, but in no way absolves these light bulb manufacturers or this printer manufacturer from protecting, from doing things like updating their firmware and using all the appropriate best practices for secure coding. But the goal here is to apply access lists so that this guy doesn't even get to attack these guys, and that's your added layer of protection. So how is this built out? Well, we have a tool called mudmaker.org, which builds this out, right? You can enter in just some information, what sort of access is needed, whether the device speaks IPv4 or IPv6. Those of us who are participate in ACM activities love IPv6. The rest of the world, it's still a little iffy, but as you can see in that example. So we generate a file out of that. The file has to be signed or should be signed and provides this abstract description. We can then take that description, give it to deployments, and they, in fact, not only can they apply access lists, but they can visualize the access that the device says it needs. This is a tool built by Vafa and Alibi at Indiana University called the MUD Visualizer. It's all on GitHub, by the way. You can pull this stuff down. And this is basically a bit of an introduction to the idea that a manufacturer usage description can provide some information to a local deployment in terms of understanding the device's needs, both in terms of network access and for other purposes. What might those other purposes be? If you might have noticed that President Biden issued an executive order that said that device manufacturers should provide software bills of materials to their customers. Well, how is a network manager going to locate where the software bill of materials is? Well, MUD provides a good way to say, hey, here's where you go get that SPDX file or a Cyclone DX file, or that describes the contents of this device from a software perspective. Maybe from a wireless perspective, we can say, well, here's a certification of what frequencies this device should use and how many dB should be, you should hear this thing at such a distance. You could provide that sort of information, or other forms of certifications that this device has, say, for instance, UL certifications, CE certifications, or FCC certifications. Or your idea here, because it's a mud is merely JSON with a little bit of syntactic sugar that you can use to describe other characteristics or needs of the device. And of course, the nice thing about references is the fact there are so many of them. With that, I'll stop.